SwayamPrabha. Digital India. Educated India.
Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Power Plant System Engineering, Module 2, Vapor Power System, Part 3. So, in the lecture, we will start a new segment, that is fuels and combustions. So, here in steam power plant, the fuel is main source of energy, and the type of fuel that you are using here is mainly fossil fuels, that is coal. So, basically in this lecture we will try to see what are the different variety of coals, their grades, coal analysis, then what is the method of coal firing, and although there are many methods of creating combustion in the furnace, but one of the best method is the fluidized based combustions. So, we will discuss about that combustion technology in this lecture. So, let us start the first segment, that is fossil fuel, that is coal. Now, let us see, if you look at the modern steam generator, we require the source of energy to generate steam, and for that we need some combustions of fuel and air. So, if you look at this particular figure, to get steam steam from water, we require the heat source from the fuel which is fed at this location. Now, this particular fuel generates, after combustion it generates flue gas, and in the entire circuit the flue gas goes to the atmosphere through the stack. So, the fossil fuel steam generators are mainly dealt with the working fluid, which is water or steam, and this steam production is achieved through flue gases, and flue gases are produced by combustions using variety of the fuels. One can think of solid fuel, liquid fuels, and gas fuels also, but most efficiently in this case we treat the combustion as a solid fuel, that is coal. So, if you look at in general the fossil fuels, they generate in the earth through slow decomposition of chemical conversion of organic materials, and they are mainly available in the basic forms, either in the solid form, liquid form, which is oil, and natural gas. So, solid most fundamental way of availability is the solid fuel, that is coal, and this coal is a classical source of fossil fuel energy resources, which is responsible for 50% of electric power, while we use these natural gases, they contribute 30%, and remaining part comes from the renewable sources, hydraulic or nuclears. So, essentially this 50% of electric generations is achieved through fossil fuels. So, either it can be in solid form, liquid form, or natural gas form. But there are new combustion fuels which includes mainly liquid and gases. They are derived from the coal, oil shale, and tar sands. So, in fact, there are some byproducts that come out of solid fuels, that is coal, and they are called as a synthetic fuel, and they are mainly used in the industrial and domestic waste, but that is not part for analysis when you deal with the modern steam generator power system. So, let us discuss some history about the coals, its types. So, the coal is the common term that is used in large sense, and it caters solid organic materials with wide variety of composition, properties, and they are rich in one particular element, that is carbon. So, basically the carbon is the main constituents. The classification of the coal is based on the physical and chemical properties, its grades, rank, and the lowest one is called as lignite, highest one is called as anthracite. So, first highest grade coal is anthracite, and it contains highest carbon contents close to 86 to 98% by mass, and they have a very less volatile matter, that is difference out of 100. If 86 to 98 goes as a carbon, rest of the contents like volatile matter is between 2 to 14%. So, they can be sensed by their color, which is shiny black, they are dense, hard, and they are very brittle cold, and its heating value is approximately 25 megajoule per kg. When you talk about the next grade, that is called bituminous coal, which is the largest group, that means its availability in the earth is the largest components, and they contains mostly 46 to 86% of carbon, 20 to 40% of volatile matter, and when they are used as a pulverized form because they contains more volatile matter. But whereas anthracite can be taken as direct coal that can be burnt easily. But these bituminous coals, they have heating value in the range of 25.6 to 32.6 megajoule per kg. The next category which is called as a sub-bituminous coal, and for which the heating value further drops, which is 19.3 to 26.8%, 20.8 megajoule per kg, and they have relatively high moisture content. Lignite is the lowest grade coal that resembles the laminar structure of wood fiber, and they have highest moisture content, which is 30%. Heating value is further less, that is 14.6 to 19.3 megajoule per kg. And peat is considered as the lowest, or peat is considered as the waste from the coal, and the word peat is used, that means when the coal formation starts in the earth, its first form is the peat, and then it is further decomposed with plant matter and inorganic materials with 90% of moisture content. So, it starts with peat, then starts with lignite formation, and slowly it goes to the highest quality coal, that is anthracites. So, essentially speaking, this is the history of coal formations starting from peat, which is of course a non-usable form, then starts with lignite, then sub-bituminous, bituminous, and anthracites. So, this is how the coal formation takes place in the earth core. Now, let us understand when you use the coal in our steam power systems, we have to understand that how this coal can be effectively used. One way to use this coal is direct form, like as a solid structures, other is in the pulverized form, another category is most powder forms. So, in order to make highest efficiency, the powder form is the best. But again, depending on the quality of the coal, either whether you are using anthracite or bituminous coal, depending on that nature of the nature or type of the coal, we start thinking of using whether it is in powder form or it is directly in a pulverized form or like a solid form. So, to do that, what the first thing that we do, that means what is the quality of the coal, to know that we do two types of analysis, which is based on mass percentage, just to find out what I mean when the coal is used, what is its grade, what are its characteristics. So, we call this as a two types of analysis we do, one is proximate analysis, other is ultimate analysis. So, in the proximate analysis, what we do, it gives the ready meaningful information about the coals used in the steam generator. It determines the mass percentage by fixed carbon, volatile matter, moisture, and ash. So, fixed carbon is the elemental carbon that exists in the coal. So, it is nothing but the difference between the original sample and some of the volatile matter, moisture, and ash. The volatile matter is the portion of the coal which is driven off when the sample is heated at 950 degrees centigrade per 10 minutes. That means, if you in the absence of oxygen, if the coal sample is heated to 950 degrees centigrade per 10 minutes, then we can drive off this volatile matter. Then moisture can be determined by a standard procedure in drying in a oven. Ash is the another kind of organic salt that is also present in the coal, and it is considered as a non-combustible residue So, that has to be dried off, and to do this drying test we must do it at 750 degree centigrades in the absence of oxygen for 10 minutes. Sulfur is another culprit because it produces sulfur dioxide after combustions, but it is combustible and this contributes to heating value of the fuel, but it forms oxide that combines water to form acids. So, and this is the main cause of corrosion and environmental problems. So, corrosion issues are normally highly possible in various components of steam power systems. So, the sulfur has to be decomposed during its burning process. Now, next category of this thing analysis is the coal analysis, is the ultimate analysis. It is based on the scientific evidence or test that provides the chemical elements that comprises of coal together with ash and moisture. So, on a mass basis the elements are obtained as carbon, hydrogen, oxygen, nitrogen, sulfur, moisture and ash. So, basically 100% mass by coal contains these components, and from our analysis we must find out each of the component. So, dry and ash free analysis of combustion basis, because if you just remove this moisture and ash, then basically on combustible basis only this part take the lead during the combustion process, like moisture and ash they are just have to be driven out. So, essentially speaking, out of 100% by mass, if you take out m plus a, then that is the most rest amount is the usable form of coal. Now, another parameter while using this coal is to find out the heating value of the coal. So, it is nothing but the amount of heat that is transferred when the products of complete combustion of coal samples are formed and subsequently they are cooled to initial temperature of the fuel. So, there are two types of heating value, one is higher heating value or gross heating value, other is the lower heating value. The main difference between these two is nothing but the latent heat of vaporization of water. Like during combustion process, if there is a vapor formation, then the lower heating value does not take into account that. So, it has to be added with lower calorific value to obtain the higher heating value of the fuel. Normally, why this latent heat of vaporization word is there? Because at the end of combustions there is formation of water. Normally the gases are not cooled down to dew point temperature of the steam generator, because if they are cooled down to dew point temperatures, then there will be formation of water vapors. So, dew point temperature is also a critical parameter that has to be estimated during the combustion process of the coal. So, to do these things, all the analysis like to obtain this standard heating value of the coal is mainly desired, and it is mainly based on the energy balance and efficiency calculations. We will try to see how these values are calculated in the subsequent problem. Just to keep more precise, that for the calculation point of view, if you talk two values, one is lower heating value which is higher heating value minus the latent heat of vaporization for water, that is nothing but mass of the water vapor in the products of combustions per unit mass of the fuel. HFG is the latent heat of vaporization for water. Now, if you look at water like content like H2O, H2, because their molecular weight falls in the range of 1:9. So, basically instead of talking about mass of water, if you talk in terms of hydrogen, it is 9 times mass of water. So, this is another way of looking at the calculation of lower heating value of the fuel. Estimation of these things we can do in this method as well, because if you look at here, the coal also contains hydrogen and this hydrogen takes part in this combustion process to form the water. So, that is the reason instead of taking directly of water, we take hydrogen into account to calculate this lower heating value of the fuel or coal. So, there is a standard formula which is called as Dulong formula, which gives higher heating value of the fuel, but its unit is BTU per lbm. So, if you use these expressions, like if you want to calculate a higher heating value of the fuel in BTU per lbm, then that is equal to 14.6 C plus 62,000 into H minus O by 8 plus 4050 S. So, this is a very standard formula which can be directly used to calculate the higher heating value of the fuel. So, once you know higher heating value and once you know the latent heat of vaporization, then it will be possible to calculate the lower heating value of the fuel. Now, let us see that once you have this information of quality of the coal, then let us see that how we are going to use effectively in a steam power systems. So, if you look at particular figure here, essentially this is a pulverized coal firing systems. What we have is a raw coal forms from the bunker and it is fed through the feeder and it goes to this firing system pulverizer. So, in a pulverized form of the fuel that goes and enters into the fuel burner. So, basically to push this fuel or this coal into the fuel burner, we require a fan that pushes these things here. Then it enters to the burner box and coal firing starts. So, combustion takes place here and heat is released on this boiler front face. But again, any kind of unwanted things, like if there are some particles which are not burnt completely, then again it comes back through another route and enters through this primary fan route and goes to the pulverizer unit. So, this is how for the best possible way or efficient utilization of the things we use in the pulverization form. But if you start looking at the history, it starts with earlier with a manual feeding, then mechanical stoker, that means manually we can make it's in a smaller or medium size coal you have to form, and these stokers are designed to feed the coal continuously into the furnace by moving it in a grate and remove the ash from the furnace. But since this is not an effective way of doing this coal firing, so the people start thinking of pulverized coal firing methods. So, they are crossed into fine powders and they are mainly suitable for high grade coals. But what we see is major advantage for this pulverized coal firing method is that they have the ability for usage of any size of the fuel. They are good variable load response. They have lower requirement of excess air for combustions. They require less fan power. They require lower carbon loss. That means, if you use pulverized coal firing, then there will be lower carbon losses, lower operation and maintenance cost, then higher combustion temperature and improved thermal efficiency that you get out of the fuel burning. Then there is a possibility of design of multi-fuel combustions. That means, this pulverized method of coal firing can be integrated with oil, gas as well. Then moving further, there are more developments in the pulverized form of coal firing. People start using cyclone furnace. So, this cyclone furnace is nothing but a similar unit of pulverizer, but what is main difference is that the pulverized form coal becomes a powder, and this cyclone furnace creates a centrifugal motion of this powder form at a very higher speed, that means 80 to 100 meter per second, and when this mixing takes place with air, that means coal plus air mixing takes place at a speed of 80 to 100 per meter per second, it has proved that complete combustion or combustion efficiency can be enhanced. And what additional advantage it gives? They are reduction in the furnace size, reduction in the fly ash contents, like when you get out the flue gases, the fly ash contents is less, and that is saving in the pulverized equipment. So, with this continuous development starting from the manual feeding to pulverized coal firing to cyclone furnace, but the most recent technology or current technology of coal is fluidized bed combustions. So, here main intention of the idea is that we are creating an environment such that the coal, although it is a powder form of the coal is a solid particles, it behaves as a fluid during the combustion process. How it behaves as fluid will come back in the subsequent lectures. and subsequent slides. So, let us see that what is the concept of fluidized based combustions. Till date, this is the most recent technology, and here we are intended to think that how these coal particles can behave as a fluid. So, in this combustion process, the crushed coal particles are injected into the fluidized base, so that it spreads across the distribution of grid. So, what we look at here, that if you refer this particular figure, we have a furnace, and that is called as fluidized bed combustion chamber. So, this is the fluidized bed combustion chamber. In this fluidized bed combustion chamber, we have submerged tube banks that contains the fluid, or in this case it is water that has to take heat from this through this combustion process. So, this submerged tube bank is nothing but water tubes. Then we have this furnace wall, and there is a convective tube bank, that is another case, that means another circulation of tubes where the convection of the heat transfer from the fuel to the water goes through the convection mode, and they are called as convective tube banks. And this why this water comes, and finally this is what we call as steam drum, and ultimately we get the saturated steam in the steam drum. But what our main intention is not about this formation of steam at this stage, rather we will try to link that how we can achieve this fluidized combustions. So, what happens here, if you look at this figure, we have the coal and limestone feedstocks. So, why do we require limestone? Because we also require that sulfur contents has to be minimized, or effect of sulfur for the formation of SO2 has to be minimized. So, we have a coal and limestone feedstocks that enters into the supply line, and we have air fan, and all this coal and feedstock they goes in the powder form. That means, it is we use a cyclone furnace to create a powder form of the coal, and which enters into the combustion chamber. Now, here this fluidization combustion takes place. Now, how this fluidization takes place, if we come back here. Now, let us see that when there is a no combustions, we have a stock of bed, that means we have a stock of bed which is called as a coal bed, which are the collapsed state, and it has certain height. That means, the powder form of the coal is contained in this for a height H0, that is initial height. Now, this bed has to be make a fluidized bed form. So, what you do, you allow this air, mainly that is fluid in means this is air at a very high velocity, so that entire stock becomes fluidized. That means, it pushes the coal particles or collapsed state of this coal powder form to a fluidized form, and it goes out. So, basically a beginning state it is a collapsed state, and during fluidized states it becomes particle form. So, essentially there are three densities involved. One is density of the bed, then density of the fluidized form, and the fluid in, that is air density, which pushes these things up. So, basically due to the density difference of air and this fluidized bed and the gas particles, the necessary pressure difference is created. So, to have more efficient way of this burning, we use this combustion air through, that means combustion air is blown through some grids with and it adds some upward velocity coefficient that causes the fluid particles to become fluidized. Fluidized means coal does not become fluid, but it behaves as a fluidized form. The unburnt carbon leaving the bed is collected in a cyclone separator and returned back to the main unit again. And when this fluid out, this is basically here, this is combustion takes place. So, the main advantage of this fluidized combustion is the ability to desulfurize the fuel by adding limestone directly into the combustion bed during the combustion to meet the air quality standard for oxide formations. Now, more specifically, when you look at the fluidized bed, here we use the crushed coals of certain diameters, which is 60 to 20 diameter. And other thing is that we also require a plenum chamber or we call as air plenum which is in the bed, and that gives necessary fluid velocity. Now, for the mixing we require swirling mixing, that means fluid and air has to mix very properly in order to enhance this combustion efficiency. And ultimately at the end of this combustion, the heat that is released through this coal and air combustion has to enter into the boiler water tubes. So, the boiler water tubes located in the furnace receives heat released due to this combustions. So, this essentially this submerged water tube, tube bank and also this convective tube banks, they receive heat from this combustion. And finally, the products of combustion leaving the bed contains large portions of unburned carbon particles, and they are again collected back through a cyclone separator. The unburned particles return back to the fluidized bed to complete this combustion process. So, main difference between this fluidized bed and cyclone furnace is that in a single method one can use to remove sulfur. That means, if you use a conventional cyclone furnace, there are difficulties because in separating sulfur, but in this mechanism fluidized based combustions, there is a possibility that sulfur can be removed during this combustion process, and that is the reason this fluidized bed combustion technology is gaining more importance. And moreover, for environmental viewpoint, this method gives lower production of NOx. Now, here we will try to see that how during a fluidized based combustions, how this sulfur contents gets removed, because when you use this calcium carbonate CaCO3 with sulfur oxide and oxygen, and when this combustion process happens, we get calcium sulfate and CO2. So, CO2 anyway goes out to the atmosphere. This calcium sulfate is collected as a dry waste. So, this is how it helps that the limestone helps in getting this sulfur in, or this SO2 formation does not happen in the end here. So, had this equation was not there, probably we would have SO2 in the products and which goes to the atmosphere. Now, this SO2, and when it interacts with limestone, it forms CaSO4 and it can be collected as a dry waste. So, this is the advantage that the fluidized based combustion gives us in removing sulfur from the coal. So, here reduction of sulfur oxide can be achieved up to 90% in a fluidized bed plant, and here maximum temperature can go up to 750 to 950 degrees centigrade. Now, let us see some theoretical modeling of these fluidized based combustions. So, there are two important information that I need to share. First thing, the theoretical model for fluidized bed involves the required pressure drop, so that the coal has gained sufficient momentum to become the fluidized form, and we also require minimum velocity for the fluidization to happen. That means, initial state the coal particles they are in collapse state. So, to bring it to a fluidized state, we require a velocity which is called as minimum velocity for fluidization, and this can be calculated by equating drag force of the particle due to motion due to weight of the particle. So, if you look at this core shell of this fluidized collapse state and fluidized state, so essentially the mass that comes, which is nothing but the weight of the fluid particles, it is that can be u times rho s into g. Rho s is nothing but density of the solid particles. So, this becomes weight, and that is mass times mg. Then we can get drag coefficients by this expression. The fundamental expression of drag coefficient is nothing but f by half rho a v square u square. So, here u stands for the fluidization velocity, and here we assume these particles to be of spherical shape. for which we can find its volume 4 by 3 pi r q, and cross sectional area of the particle is pi r p square. So, equating these two, we can derive a fluidization velocity u in terms of density ratio and particle diameter. This is the main theory governing for this. But to make, and of course, we require the pressure difference. So, the total pressure that occurs in a fluidized bed consists of three components. One is pressure drop due to friction, pressure drop due to static weight of the solids in the bed, that means this part, and pressure drop due to hydrostatic head, static weight of the fluids in the bed, and this is called a hydrostatic head. So, in normal circumstances, these two components we normally neglect, so that total pressure contains only the pressure drop due to the static weight of solids in the bed, and this is nothing but rho g h. Rho g h we can find out, but here we have to introduce a parameter what is called as a porosity or void, that is alpha. So, average porosity or void fraction of the bed in the fluidized state. That means, when it becomes a fluidized state, you can find there are not entire unit or entire area is filled with all the coal particles. There are voids in between. That means, when the coal is powder form, it goes off, and in this dome, then what happens? You will not find that entire area or entire unit is covered with all the particle of the coal, but it contains coals as well as some voids. That means, there is no, in this void means there is no coal. So, those void part is also has to be taken into account while calculating this h, that means how long means what is the height of the fluidized bed, that is h. So, when they are in collapsed states, we call this as a porosity is alpha 0, this is in the order of 0.4. Now, when they are in the fluidized state, this value also goes up. So, one fundamental linear relations we can obtain, that is 1 minus alpha by 1 minus alpha 0 is h 0 by h. So, this will give you necessary pressure drop. So, you can find out delta p by h for, that means we normalize this, we can find the expression delta p by h from these equations. So, this is how the working equation is all about. Now, to calculate the minimum fluidization velocity, we need to introduce the term called as a non-dimensional number, which is called as Archimedes number. And for a fluidized bed, if you want to calculate what is the voidage, and for a working range of fluid particles that has to be involved, and third thing, what is the minimum fluidization velocity, all these things can be calculated by a simple expressions which we need to introduce called as Archimedes number, and this Archimedes number is defined by this parameter AR is equal to rho A into rho S minus rho A g dpq by mu g square. So, if you look at here the terms associated with this, mu g is the viscosity of air. So, it is mu A, okay. Mu A is the viscosity of air, and dp is the diameter of the fluid particles, rho A is the density of air, rho S is the density of solid, and rho B is the density of the bulk density of the bed. So, first thing that we need to calculate is the void fraction, which can be correlated with respect to density, that is 1 minus rho B by rho S. Rho B stands for the bulk density of the blade, and rho S stands for the density of the solid, because we have two density. When the entire coal products sits on the bed, we have certain density, and but each coal particle has own density, that is density of the solid. So, then fluid drag can be estimated by this equation, that is delta p times A. So, this can be correlated with A times H into 1 minus alpha rho S minus rho G. So, we can calculate what is delta p by H. Then also we can introduce Reynolds number. So, why this Archimedes number is related? Because to find this minimum superficial velocity. So, essentially superficial velocity is the gas flowing through the fixed bed reaches the minimum value. So, when you are pushing this air into this bed, we reach this air velocity to a minimum value to achieve this fluidization state, and that is called as fluidized velocity, and this can be related through this Rayleigh number, that is Re is equal to rho A dP times um divided by mu. So, this Re and Archimedes number for the fluidized states can be represented by these equations. So, essentially Re is equal to C1 square plus C2 into air to the power 0.5 minus C1. So, C1 and C2 are fixed number, and this relation helps us to find out what is the fluidization velocity or minimum superficial velocity which is required to obtain this fluidized state. So, this is all about the fluidized bed combustions and its term technology, and I have not gone deep into these particular segments, but I have just give the summarized view of the coal combustions through fluidized bed technology in a efficient way for a modern steam power unit. And finally, before I conclude, I will just give some summary of these fluidized bed combustions. There are many advantages of these fluidized bed combustors due to its low temperatures. That means, through this fluidized bed technology, inferior grades of coals can be handled because we are bringing them into fluidization state. Carbon and ash carryovers on the flue gas do not cause any kind of harmful effect or fall in the heat transfer process, and there is a substantial reduction of emission of oxides of emission, that is NOx reduces drastically. The construction becomes economical due to cheaper alloy materials and requirements, and there is absence of pulverized equipment that adds further economics. So, basically these four advantages has necessitated the fluidized bed technology in a large sense. The fluidized bed combustions can be designed to incorporate boiler within the bed, and through this fluidized bed technology, the volumetric heat transfer rate can be increased about 10 to 15 times, and at the same time surface heat transfer rates is also higher by 2 to 3 times as compared to conventional boiler technology. And more advantage is that they can be integrated with combined cycle steam power plant. Normally fluidized bed combustors are used Rankine cycle for steam power generations, and they can be linked to combined power systems that involves Brayton and Rankine cycle. And more specifically, it also caters the need of these steam power systems which works up to 170 bar and 550 degree centigrades, and it can handle the fuel flow rate of 40 kg per seconds. Hence, the fluidized bed technology becomes a attractive alternatives for power plant applications. So, this is about fluidized bed combustions. So, based on our discussions, we will try to solve some numerical problems. So, the first problem is based on the ultimate analysis for the coal. So, the ultimate analysis of the coal, that means we are using a bituminous type of coal, and this ultimate analysis gives different compositions: carbon as 80.7%, hydrogen 4.5%, sulfur 1.8%, oxygen 2.4%, nitrogen 1.4% and water 3.3%. So, we are asked to write the combustion equations, calculate HHB, LHB and dew point temperatures. To solve these problems, first let us start, we call this as a relative mole fraction. So, relative mole fraction means we start with carbon. So, basically we have carbon plus hydrogen plus sulfur plus oxygen plus nitrogen plus water. Now, we have carbon 80.7%. So, I will write 80.7 divided by molecular weight of carbon, that is 12. Hydrogen 4.5%, so I write 4.5, its molecular weight 2. Sulfur, its molecular weight is 32, it is 1.8 by 32. Then oxygen, that is 2.4 by 32. Then nitrogen 1.1 divided by 28 molecular weight. Water 3.3 divided by 18, its molecular weight. So, if you divide it out, then we can find out it is 0.725 C plus 2.25 H2 plus 0.05625 S plus 0.075 O2 plus 0.3929 N2 plus 0.1833 H2. But for a stoichiometric combustions, we get CO2 plus water. Since we have sulfur, we have SO2 and we have also nitrogen. So, this fuel has to be mixed with N2 plus O2, because N2O2 means this is air, to give rise to this, but we do not know the composition of quantity of N2 and O2 requirement. So, for that we have to do this H2 balance. H2 balance, if you see here, H2 is 2.25 and it will give you water here. So, it is 2.25 plus this 0.1833. So, this will give you 2.4333. So, H2 balance it gives, then we have to give sulfur balance. Sulfur stands as here and it will also give SO2. So, that sulfur balance, same sulfur is being used this, that means sulfur will have in the product as like is 0.05625. Then we have oxygen balance. So, oxygen has two parts, one is products and reactants. So, the products component will have 0.725 plus 2.25 by 2 oxygen here and oxygen here plus 0.05625. Reactants will have oxygen from this side, that is minus 0.075, this part. So, the balance amount that will come from oxygen here would be 1.83125. So, we got this number. Then oxygen you get N2 balance. So, N2 balance, if you look at air, it gives 3.76 moles of N2 per mole of O2. So, this means 3.76 into 1.83125. So, this is 6.8855 N2. So, doing this N2 balance, we can write this complete equation as 0.725 C plus 2.25 H2 plus 0.05625 S plus 0.075 O2 plus 0.03929 N2 plus 0.1833 H2O. Then these two component N2 will be 6.8855 N2 plus O2. O2 is here, so it is 1.83125 O2. So, this gives products like these three terms, that is 0.725 CO2 plus 2.433 H2O plus 0.05625 SO2 plus 6.92479 N2. So, this is the combustion equations. Then we can recall Dulong formula. Which says HHB is equal to 14,600 C plus 62,000 H minus O by 8 plus 4050 S. By looking at this percentage numbers, we can get HHB is equal to 33.6 megajoule per kg. Now, we also require LHB and dew point. So, to do that, we need to find out the partial pressure of water. So, to get this partial pressure of water, first we have to find out the mole fractions. So, the mole fraction of water is 2.433 and total mole fraction contains 0.725, that is in the products. Plus 2.433 plus 0.05625 plus 6.92. So, putting this number is 0.24, and you have to add, if you say atmospheric pressure. So, this atmospheric pressure as 1.01325, then this becomes 0.24 bar. So, at this pressure use saturated pressure table. So, this will give you T saturated temperature as 64.58 degrees centigrade, and correspondingly we can find out HFG. HFG is 2347.2 kilojoule per kg, and knowing this enthalpy value, we can find out LHB is equal to HHB minus HFG. So, 33,600 minus 2347.2. So, this LHB is approximately 31.3 megajoule per kg. And since this we require dew point temperatures corresponding to the saturation temperature, we can call it as DPT. So, dew point temperature is 64.58 degrees centigrade. So, with this I conclude. Thank you for your attention.